Then we have all right.
Good morning. Great to be here. Nice to see all of you here, all familiar faces. So my name is Tatu Harviainen. I'm using technical research suite at VTT Technical Research Center Finland. And we have been one of the research organizations taking part into the Necoverse project, which has been really interesting and nice opportunity for us to work on some of the topics related with the Metaverse. And our focus has especially been on the technology side of things. And I will talk a little bit about how we see the Metaverse and technology, and then giving some examples of technology topics that we have worked in the project together with the environment. So our take on the Metaverse is mostly on the industrial Metaverse side. We are interested in looking at how this technology can be used in an industrial setting. And from our point of view, the industrial setting has a little bit of a specific requirements for the Metaverse. Especially it requires tight combination of the physical and the virtual world. You usually want to use the technology to somehow work on topics that have real world counterpart. So a little bit different compared to the, for example, entertainment use of Metaverse technology. And that impact goes to the whole technology stack. So from the input side, you usually want to have the connection to possibly the design data, the real world data coming usually from the sensor, and also different kind of enterprise systems such as Internet of Things data coming from the environment. Please go.
Yes. How do you see the development? Do you see that there will be a kind of a industrial Metaverse platform and the kind of gaming platform? Or are they separated or can they be same?
At least how it seems based on our investigation into the areas that they are a little bit separate. There are components that are kind of used across, but the overall system is probably kind of a little bit different kind of based compared. Yeah. But on top of the input data, you need the platform that does the data management, and on top of that you usually have the user interface and the multi-user collaboration features that are kind of application specific. And if we compare that to how we have been considering the spatial computing pipeline as we are a research team working on the spatial computing, it looks quite a lot the same. So this is kind of an interesting area for us to work from this point of view as well. So in the spatial computing context, we have often used this pipeline to describe how we see the data processing at different levels. So we are working with different sensor modalities, mainly imaging sensor data, getting the kind of a sensor understanding or the data from the environment. We are working with autonomous platforms, looking at how we can use them to carry around the sensors in the environment. And the focus is in the data analysis, how we refine that sensor data into information, some kind of situational awareness of the operational environment. And on the output side, you have the data visualization, and there we have been working with the immersive data visualization mostly, so augmented reality and virtual reality. And the things that we have researched and developed in the project on the enabling technologies, or the kind of the core or the bottom layer, we have been looking at especially technologies, how we can create the copy of the virtual or the real world easily. So we have been inspecting Gaussian splatting for this, and then we have been working on also method for connection between the real world and the physical, the virtual world, by looking at technology, how we can know from the sensor data where the sensor is in the real environment, and that way have the same location available from the virtual copy. The Gaussian splatting is a relatively new technology. The idea is that instead of modeling the environment or doing kind of a actual geometry capture, you collect a big sampling of the environment using just RGB images, and then you use neural network that learns how those individual images are turned into an understanding of the environment. So what is the relation between the images and the features that you see in the images? And it kind of creates this sparse point cloud of the environment with the mapping of the color data into that.
How is this different from photogrammetry?
This is different in that sense that photogrammetry, you create like a traditional geometry from the images.
Yes,
But with
please.
this, you have kind of a sparse sampling that is not geometry as such. So it's much more lightweight. Yeah, and enables free navigation in a way that it gives highly photorealistic results. So it can generate, for example, the reflective part of the lighting from all of the viewpoints, whereas compared to the photogrammetry construction, you get just the geometry.
But do you get the geometry this way also?
Not as sparse.
I need the geometry.
So I need the dimensioning.
Yeah.
The other dimension.
Yeah. You can get the dimensioning, and that is something that we have worked on. So we have been looking at how you could use not only the RGB data, but RGB depth data, and that way you get the scale and be able to do accurate measurements as well. But the benefits of this is that you don't need to do modeling that is specific for the platform that you know that you can render it on. You just throw a bunch of images and you get this kind of way to inspect it with a high quality, and it's lightweight, so you can deliver it, for example, over as a web page to customers. Then image-based localization. We have been working on a method where if you have a point cloud captured with the LiDAR from the operational environment, using that data, you can determine the position of any camera in the environment very accurately. So here is an example of that, where you change between the point cloud representation and an image taken from the camera, and it automatically aligns the camera image to the point cloud.
What's the accuracy that you can achieve?
Centimeter scale, I would say.
Okay.
We haven't done that kind of like thorough benchmarking yet, but the results are good. And what is especially good, it's very tolerant to the changes in the environment. For example, here you see that the table is in completely different location, also changes in here. But if you look at the static geometry, it's very accurate.
2 minutes.
All right, speeding up. So that's kind of core enabling technologies. Then we have looked at the platforms. We have been kind of going forward, made a decision that we will focus more on the NVIDIA Omniverse, which we feel that is most ready and most capable for industrial use cases. It has good integration with many of the industrial design tools, for example. We have worked with the game engines. Usually they are some kind of a component in that whole system, for example, integrating with the Omniverse to visualize the data. And we are going to investigate Nokia RXRM going forward. It's completely different approach. It's more about kind of just streaming what you see in the real world, but there might be interesting opportunities there. And lastly, example of the top layer that you have been working on. This is one of the pilot cases in which we have developed a solution for enabling efficient remote collaboration between the operator in the field using augmented reality glasses. So from the glasses we stream the video data to the remote inspector, so they have the same view as the operator in the field. And then we have the operator user interface where the operator can take snapshots from the scene, add virtual annotations to that, or the remote operator with the augmented glasses can do the same, add annotations or notes to the environment. So kind of a very simple things in there, but already this enables very good collaboration between the operator and the field and the remote operator. So that's very interesting. Probably we hear a little bit more about this on the later presentation. And that concludes my presentation, hopefully in time.